Hi, I'm Ali and I want to explain an innovation in optical technology, controlling solitons using Cherenkov radiation. Solitons, what are they? In mathematics and physics, a soliton is a self-reinforcing single-wave packet that maintains its shape while it propagates at a constant velocity. Physically, they're produced by an optical microresonator, which is a small ring which takes in a single high-frequency laser to produce a signal of multiple frequencies. And these rings are tiny. At 100 micrometers diameter, you can fit 100 on a small area of a single penny or a 25 centavo. A team led by Dr. Cheng Ying Bao at Purdue University showed that you can generate single solitons passively using Cherenkov radiation in a recently published article in the journal Optica. The problem with creating single solitons is that they're very hard to do. You're more likely to create a noisy signal because of the uncontrolled pulses, and Cherenkov radiation contributes to this noise. Cherenkov radiation is the light equivalent of a sonic boom, where a light particle travels faster than the rest of the light in the medium it's in. This boom disrupts the soliton generation and creates several signals. But the researchers at Purdue University have shown that if timed properly and if microresonators are generated in a specific manner, Cherenkov radiation can actually aid pulses to propagate single solitons to create a smooth frequency comb. Solitons have been known theoretically since 1834, but it took 131 years before they were experimentally produced. The microresonators they used were made of silicon nitride, which has an ideal band gap of 5 electron volts for light absorption and is compatible with silicon chips. The Damascene process of creating microresonators relies on etching preformed molds, which are then coated with silicon nitride to produce the micro-level rings. What the group did differently was that they used an experiment where device 2 has a gap width of 300 nanometers while device 1 was of 500 nanometers, and device 2 was characterized to have a weaker spatial mode interaction compared to device 1. They measured the frequency chromes to reveal that device 1 produced a single soliton while device 2 produced 5 solitons, which was further proven by power scans which are shown in the graphs above. The first patent filed for microresonators dates back to 1970, which relied on lateral waveguides and not ring-shaped cavities. The latest granted patent makes use of ring-shaped cavities for creating a low-noise and high-power tunable or fixed wavelength laser. The concept is applicable to both an integrated laser or a hybrid integrated version using a filter and a separate gain chip. Once you've mastered the creation of solitons, you can apply it in several fields, starting with optical communications, where you can use it to create more accurate optical clocks, or to create astronomical spectrograph calibrations, or even LiDAR. You can also use it as precision sensors, so you can detect random molecules in the air or in your water samples. And because of the use of silicon in the production of these microresonators, you can actually integrate it into your miniaturized chips and have a future wherein you have a high precision microresonator installed in your cell phone for further applications.